All right. So we were kind of wrapping up last time talking about ways to kind of prevent exposure. So if you're working at a facility, right, you can either keep away from things, right, kind of keeping your distance back, keeping distance or kind of putting stuff in front of you. So easiest way to avoid exposure, kind of the farther away things move. Lab this week was kind of looking at that, right? So you looked at lab, you had the source really close by, it beeped a lot, and as you move farther away, it beeped less often. You saw the graph kind of go down, and you probably saw kind of a scale where it kind of went from essentially really high, but the farther you went, the lower it went, kind of like a log or inverse pattern, kind of a shape like that. So kind of when you're really close versus kind of further away, and even like short distances, you saw kind of a fast drop. So if you moved it 1 centimeter or 2 centimeters away, you had a really high counts, maybe in the hundreds. But then as you go farther and farther away, you go from hundreds to maybe 50s, even to tens. And if you went too far away, actually, you might not have even noticed anything after 30 seconds for lab this week. So that was just kind of emphasizing that point. The farther you are away, the less exposure you're going to get. And then if you can't do that though, right, we couldn't do that all the time. There's other ways to prevent this too. You can also kind of put other stuff to get exposed instead of you. Lead and concrete and heavy materials work the best, really dense things. But even stuff like water can work. So water is a pretty dense material in terms of material wise. It's just also, and it's very heavy, but it's just also very bulky. So using large amounts of water as a source may not be the best way to protect yourself from materials, just because you'd need a lot of water there. Water doesn't hold together, but either blocks of ice or just big buckets of water have been used as storage protection in the past. And actually, if you go to a nuclear power plant, and you were to look around, one of the things you'd see at that nuclear power plant is the storage facilities for the radioactive material, which actually is just giant deep swimming pools where they store all the stuff at the bottom. So the water between you and the source prevents you from being exposed. And if you're in the water, you can actually be relatively safe away from that without being exposed unless you get really close to it. But otherwise, we're going to store stuff in lead containers, heavy duty containers. So if you're working with radioactive material, one of the things you'll notice is the boxes they come in are often very heavy because they're made of lead. The lead is preventing the material inside the box from escaping and getting out into the environment, releasing those particles, releasing those rays there. But the stuff is useful for various things. When you're working with radiation, you want to kind of beware of your exposure. We don't need to know specifically about, for our class, what we're using. But there are different ways of recording your exposures. And if you are working with these types of things at a hospital, at a facility, at a company, just make sure you know what standard of measurement they use. Because just like when you drive here, it's miles per hour. But when you go up to Canada, it's kilometers per hour. If you know the speed limit is 60, one of those is really fast and one of those is not so fast. One of those will get you a ticket, one of those won't. So knowing which unit they're using, same thing for when you go to a company or a hospital or whatever, know what your exposure standards are, know what the good numbers are, know what the bad numbers are, because 50 of one unit versus 50 of another unit is not so bad. So 1 rad is really bad, 200 SVs is really bad, but 1 SV is not so bad. So kind of knowing the scales for wherever you're working, we're not going to have to worry about that for our class, but in future use, just kind of to keep that in mind. And then if you do work at a place like this, right, how do they know how exposed you are? How do they know if it's safe or not for you to be there? A couple of different ways to do that. One of the easiest, most simplest ways is actually they just give you a little badge that has a piece of film in it made of X-ray sensitive film. And just like with a color film camera, if light hits the camera, hits the film, it turns the image darker. So that's how old cameras work before digital design. And what they did is they just decided that they keep a little piece of film in a piece of badge and a little plastic thing. And you wear that all the time. And every week or so, they take that piece of film out, they develop it, and they see how dark it is. And if the film's really dark, it means you've been exposed to a lot of radiation. If the film's not so dark, then you're okay. You haven't been exposed too much. And it's just a really passive way to record because it doesn't have any moving parts, nothing to break. So if you do work at a place that uses those, they're usually built into your name tags. Try not to lose it, just wear it all the time. It's just a really kind of simple way to tell. Only issue with this is that you could be exposed to a lot of radiation and they're not going to know until they check the badge later. So you can be exposed on Monday to a lot of stuff. They don't check it till Friday. They don't tell you till next week. Oh, by the way, you got exposed to a lot of things. So we got to kind of adjust your dosage this week to make up for it. So it's not that useful for kind of on-the-spot emergency response. It doesn't tell you right away till later. But things like what we used in lab this week do. So you can buy little detectors, and you can get little ones that are the size of the ones we had in lab. You can get little bigger ones. You can even buy ones that clip to your watch or clip to your pocket like a phone would, or kind of like a beeper pager thing. And they just kind of tell you the amount of levels at real time. A lot of time those don't have counters or anything. They don't have a kind of tracker. They just kind of tell you at once. But nowadays you can even buy ones that track. So like in lab today, we had ones that told you at a given time, but they could also monitor over time and kind of give you a history as well for a couple hours or a couple days, depending on the computers. But there's ways to detect this, because otherwise it's invisible, right? It's particles that are invisible, matter that's energy, nothing visible light-wise, other than getting sick. But you don't want to be able to tell you got exposed because you got exposed so high you're sick. Much rather tell you much earlier on if you're exposed or not. And overall, using these types of techniques, we can actually kind of give overall scales for when you get exposed to various things, because there is radioactive material all around us. And this is just kind of showing some levels of radiation that you may see. Bananas themselves, right? Bananas have potassium in them, and potassium has trace bits of radiation. So 1 in 40 elements of potassium have a radioactive version, the 40 versus the 39. Most of the potassium you ever deal with is the non-radioactive, but every once in a while you get exposed to a radioactive isotope of potassium. It's just naturally occurring. And that's a little bit of radiation from eating a banana. Also, though, people are naturally radioactive. So people, I used to have that list on here somewhere. So sitting next to a person, it's about four bananas worth of material, because we're also just naturally radioactive. We breathe in carbon from the air. Carbon 1 in a million times is radioactive instead of non-radioactive. So just sitting next to somebody, you get a little bit of radiation exposure from being there. And it's okay, because you're just naturally radioactive yourself too. But very small amounts of radiation are just in the background. But versus if you were to go for the dentist, that's about eating 50 bananas all at once. So, it's a lot of bananas, but it's not that much over the whole year. Versus your daily exposure, you're exposed to about 100 bananas worth of radiation just from going around, from sitting next to a person, maybe from sitting outside, going outside, getting some cosmic rays from the sun, maybe some radiation from the ground too, especially in New Jersey, where the rocks have a lot of granite and uranium and radon and other types of materials. So we're just naturally being exposed to radiation during the day anyway, and there's not really much we can do about that background radiation, but it's way lower than any kind of accidents that have happened in kind of more recent history. So, and even just flying in the air, when you fly in the air, you get closer to the sky. The sun gives off radiation, space gives off radiation. So being in the air in an airplane for a few hours also will expose you to some radiation, as would be getting a chest x-ray or a dental x-ray. Versus kind of your daily exposure. So the key is, though, that we do try to minimize our exposure. So we're not going around and getting chest rays x-rayed all the time. We're not going out and flying in airplanes all the time, trying to keep our exposure a little bit low. But even for these bigger cases where there have been disasters and things have been released, it's still way below the amount of radiation known to cause cancer or increase your risk of developing those types of diseases. And it's way below the safety levels for people getting hurt. And even some of the more extreme things, like getting exposed to with a larger chest x-ray system, or like a CT scan where they have to do multiple scans, or having your head scanned for things like brain injuries, where they have to use a lot of more kind of powerful radiation in a shorter area. That's still way under the exposure limit for the year that has been known to cause issues, way lower than the amount that actually has been known to actually be fatal. So people aren't usually being exposed to very high amounts of radiation, even from things like more extreme versions of exposures there. But it's also a benefit thing, right? So if you've been hurt in a car accident, they got to make sure all your ribs are intact. You don't have any broken ribs. That could cause punctures to the lungs, cause other problems, especially if they don't grow back right. They have to make sure that things heal. So they're weighing out that tiny risk versus a much larger risk, in this case, of you having a broken bone. So it's a cost and a benefit to each one of those kind of cases, making sure that we're not exposing anyone needlessly. But we use this for a lot of different things, especially for medical imaging. So medical imaging is the big one. But even things like mundane, like a smoke detector, right? Smoke detectors, fires are a risk. Lots of fires, houses burn down. Knowing if your house is on fire before it burns down is really important. and it's well worth having a tiny amount of radiation. And again, you're not sleeping with a smoke detector under your pillow, or at least you shouldn't be, because it doesn't work that way. You're not, eating the material inside this. You're not taking this up and playing baseball with it. You're not generally handling the smoke detector. It's just sitting up there in the sky, not doing anything. Yeah.
So what about like how older people have like projectors just in case for like alarms and stuff?
Oh yeah, those little watch battery, yeah, those things. So some of those older days, they used to actually especially for pacemakers, old heart machines, they used to use batteries that were made of plutonium. So the reason for that was that batteries made of plutonium last about 20 years. And you have somebody to open heart surgery, they got to get in there, they got to fix something on your heart. They don't want to have to open you up every 6 months to change the battery out. So that was kind of an idea. And they used to use them for things like really emergency phones, emergency boxes. Again, something you never want to change the battery on. But nowadays, we've actually gotten really good at making lithium batteries. So my cell phone can last a day and a half, and the battery's only half this size. Even smaller things like a AA battery or a small hearing aid battery, they can make batteries that last multiple years. Anybody have a fancy car that you don't need to turn the key on? Have you ever changed the battery in that thing? It lasts about 5 to 10 years. Eventually the batteries do die, but it's a small battery. And the same thing for those buttons for like the people that call for help, or even for some of the pacemakers now. They've made batteries that can last decades without needing to be replaced, that luckily don't need this. They're different lithium acid batteries, they're different other types of batteries instead. So they have revised to not need to use the radioactive batteries for some of those, but some people with older pacemakers, they do have the old radioactive one instead. And they usually actually have a little tag somewhere. They have usually a bracelet to warn other people about that, and also to let other people know that they have one of these things inside them, partly for medical reasons. If you ever have to operate on them, it's good to know that that's there because you don't want to accidentally break it or turn it off. But also if they were going through a security environment and maybe it comes up on a scan that there's something here, they'd want to know why that's there. You have a note from a doctor letting you know, bless you, that you have this there. So yeah, a lot of times now we're using radiation for more monitoring type devices rather than for powering the devices themselves. But the nice thing about using this for monitoring or potentially for monitoring is that you can detect diseases a lot earlier than you ever could before. So a lot of times people, if you look at cancer incidences or cancer death rates, a lot of the rate of people dying from cancer has gone down. And part of that is because they detect it earlier. So part of the reason we really stress people going to the doctors, getting various kind of diagnostic tests, whether it's, whatever type of test it is that you do for your cancers that you're at risk for. Early screening, early detection is always better. If they can detect cancer when it's still growing in only stage 2 and it's fairly local, versus if they wait till much later and it's spread throughout your body, it's a lot harder to treat and a lot harder to survive, because if it's throughout your whole body, they may miss a piece of it. And then when they miss it, it can grow back and make you sick again. So early detection for any type of cancers, and really any disease, but especially cancer, is really important. And one of the things that they've gotten really good at is using materials to actually look for cancers at an earlier age, sometimes even before you get symptoms. So a lot of times sometimes they only know they have cancer when they start to have a symptom. Something feels weird inside them somewhere, or some other element is happening, and then the doctors check out that area and they discover there's a large tumor that's pushing against this or blocking something, and that's a problem. They remove it. But if they could detect it before it got to be that big, they could remove it even easier, because smaller things are easier to take out. And one of the ways you can detect cancers a little bit earlier is by taking advantage of radioactive materials. Radioactive materials, they behave very similar to non-radioactive materials. Radioactive carbon or radioactive water is the same as regular water. Radioactive water with an oxygen 18 versus normal kind of everyday water with an oxygen 16, slightly different isotope of the oxygen, but you can drink it. You can get all your nutrients and hydration needs. You could make coffee with it. You could make iced tea with it. You could put it in, put out fires with it, make ice with it. It's going to behave the same, with the one exception that one is radioactive and one doesn't. So other than that one physical property, everything else is the same. It behaves exactly the same. And therefore in your body, it undergoes all the same chemical reactions that the regular water molecules do. And we'll take advantage of that for any atom. So if we know that cancers like water, for instance, this water would be attracted to cancers just as well as the regular water would. And the same thing for things like sugar. Radioactive sugar gets attracted to the same molecules that regular sugar does. And they've designed drugs that basically look for cancer and they're attracted to cancer because they're designed to do that. But because they're radioactive, we can find them later. So we can give somebody, if they're suspected of having some type of tumor, we design molecules that bind to tumors and are attracted to tumors, get attracted to those tumors and hang out there. And then what happens is if you were to put that molecule into a person, it would hang out where the tumors are. And you could then go around and try to look on that person, is there any spot where this molecule is hanging out? And there's a few different ways to look for where molecules hang out. But one particularly easy way would be to give that person a molecule that's attracted to tumors that's a little bit radioactive. Maybe it gives off some beta particles or even some gamma rays. And then you can, because we have good detectors that can detect radiation, we could say, okay, is there anything radioactive in this arm? No, there's nothing there. Is there anything radioactive in this head or this other arm? No, there's nothing there, nothing in the chest. But when we get down to the leg, we see there's a spot that looks a little bit radioactive because that molecule's been hanging out there where the tumor is. The other line looks fine, so you check for symmetry. You don't see the other side. But this molecule is designed to bind to tumors that are growing, and we can actually look for those tumors growing by seeing where this molecule hangs out. If this person didn't have any if this person didn't have any cancers or anything, this molecule wouldn't have anywhere to go and it would just leave. It wouldn't hang out anywhere. There's nowhere to hang out with. But in this case, they do. They had a spot that this molecule was hanging out, and that's a good sign for the doctor that there is a potential spot there that they need to investigate by surgery. Maybe they have to remove it. And then when they remove it, they can actually do this test again and see, all right, well, now that we've removed it, there shouldn't be anything left for that molecule to hang out at. And we can actually see, did it go away or is it still there? Because if that molecule is still hanging out, it could mean that we missed some cancer some cancer tumor cells during the initial surgery. Maybe we got to go back and do another treatment. Maybe we have to go back and do another operation, or however we have to kind of figure that out. But it's a way of kind of not only detecting, but also working and diagnosing after the fact to make sure you're able to do it, get everything out. And this has been used for lots of different treatments. This has been used for a lot of different types of cancers in all sorts of different systems, whether it's cancers in your brain, cancers in your lungs, various other muscle problems you can use this for. You can basically use this for lots of different diseases. And this is just kind of showing a picture, both a plant, but also this one here is right, somebody's spine, right? So somebody had spinal issues. They weren't feeling very good. They had some backaches. Wasn't sure if it was occupational. They were working in a warehouse. Maybe it was something from, just heavy lifting, doing kind of heavy duty labor. But they did a check. They gave this person some molecules that will bind to cancerous tissue. And then they checked their spine again. And it turns out there's this spot here. And that spot is from this molecule being attracted to tumorous tissues inside their spine. Normally, it'd be very hard to find this. Normally, you don't want to just open people's spines up and check every bone. Spines are really important for motion, paralysis, things like that. But now they know exactly where to look, and they know exactly which two vertebrae to go between. They know exactly where to look and cut out that spinal tissue that is probably cancerous in this one case here. This is just another picture over here of another one. Oops, yes, this one's better. And this was just another case of things that grow. Sometimes, your cancer treatments are very useful. Some materials, this was actually just giving somebody radioactive sugar. So sugar itself is attracted to anything that grows fast, right? Sugar is your fuel for your body. And radioactive sugar is fuel too. And radioactive sugar, the cool thing about that is you can actually watch where it goes. And you can see all the parts of your body that are super duper active. This brain is really active. It's red. So red is kind of fast moving and burning a lot of fuel. Blue is kind of less so. So this person's, they're alive. They're thinking, their brain's really running, and it's really nice and bright red. Their heart is also beating really well. That makes sense, right? So this person's alive, their heart's beating, that heart muscle needs a lot of energy, needs a lot of fuel, and we see that in their heart. But also we see, what else do we see there? We see some other organs too. We see some kidneys up here. We see their pancreas or something running, and their bladder. So what also happened is they're eating all this sugar. You just gave somebody a ton of sugar, and your body actually tries to do something with it, and it's trying to basically store that sugar for later. So it's processing the sugar and figuring out, okay, well, let's save some sugar for later in case we're not eating. That's why the liver's running. Your kidneys are saying, whoa, there is way too much sugar here, guys. We got to filter some of this out. So they're getting rid of it. And then they're getting rid of the excess sugar and sending it down to the bladder to get released in a few minutes. And that's all normal things you'd expect to see. But in the meantime, they also noticed in this person this spot over here. And there's no real organ, right? Your heart's on your left. There's not an equivalent organ on the right side. Turns out that actually was a tumor in this person that was unknown at the time. They were just trying to show that, look how this works great to show how good the brain works, how good the heart works. Turns out this person had a pretty fast growing tumor that was also sucking up a lot of sugar. And it was pulling in that sugar and trying to grow. And by doing a study like this, they actually could find a tumor that they didn't know was there. So using these types of methods, these what are called tracer experiments, are ways to actually detect cancers and other diseases before they actually get too big. And they can actually go in relatively early and cut that out before it's too big to be a problem. So tracers are really nicely used for that, and they have some ideal things to do. So ideally, any kind of tracer molecule you're giving somebody is going to bind to the drug. It's going to bind to the cancer molecule, because if it doesn't bind to it, there's no point in sending it through the body, right? If you want this thing basically to hunt out and find something cancerous and then stay there so that we can actually see that it's there for a little while. So you want this stuff to kind of be able to hang out in the body for a little bit. Ideally, you don't want it to be super toxic. It is going to be radioactive because that's how we're going to see it. But maybe it's not something that's super dangerous. It's not giving off tons of radiation, maybe just a little bit. Maybe it has a relatively short half-life so that it doesn't stick around in their body too long, because you want it to leave pretty quick. You don't want it to go away maybe 5 minutes, because then you're be like, quick, eat this, go run in this machine. But a couple hours sticking around before it leaves would be pretty good, because that way it's not giving off too much radiation after the procedure is done, right? You want to be able to detect this thing, give them time to drink something, give it time to circulate through their body, give it time to accumulate, give yourself time to go run that reaction, have them lie on a machine, get detected. But after that's over, after a few hours, you don't want it sticking around for days or months or years. You'd rather have it go away pretty quick after that. So kind of giving off short amounts of half-life radiation, relatively short half-life, but long enough to be kind of made and run, right? You don't want something with half-lives of only 10 seconds because you only have a minute to do everything. That's no good. But also this thing should be non-toxic, right? You don't want to go feeding them something poisonous. And also whatever it turns into should also be non-toxic, right? If it turns into a toxic molecule through radioactive decay, that's not very good either. So ideally, you're giving them something non-toxic that's able to break down relatively quickly. And the only other thing that we want to sometimes consider is that it gives off radiation we can detect, right? Alpha radiation, our skin is really good at blocking. So just like your organs are protected from alphas outside, alphas inside your body would never come out. They would get stuck in there. So that wouldn't be a very good detection device. So something like betas that can go through your skin, or even gammas, because betas could be blocked by your bones, and then you may not detect the radiation coming out. And the whole point of this exercise is to find the radiation to begin with, so we know where the cancerous molecules are. So this is kind of an example of what we may see as a radio tracer experiment or radioactive tracers. And it's used for imaging a lot of times. So you ingest a few of these molecules, you do something to kind of get them moving, and that could be ingestion orally, it could be an injection, they could do it through an IV, but they basically then just kind of look and see where does it go, and then they check it out. And there's all sorts of different molecules that can be used. You don't have to know anything specifically about these, just kind of seeing there is a whole lot. But right, what do they all have in common? A lot of them give off beta radiation, a lot of them give off gamma radiation, and most of them have relatively short half-lives. There's one that's really long, but the one that's really long is used for lungs, and it's a gas. So you're going to breathe in that gas, and then you're going to breathe out that gas a second later, right? You don't hold your breath for a really long time. Even if you hold your breath maybe 30 seconds, a minute, it's not going to stick around very long. So they can use a long half-life there because of the way the test is working, right? You're breathing out that molecule relatively quickly there. So these are just kind of some of the ways that they'll actually check for cancers in your thyroid, cancers in your brains, cancers in your bones. They can use this for other types of detections as well. They can actually even use this sometime to see how well do your lungs work, right? Breathe in some gas into your lungs. We'll actually watch them inflate, and then we'll watch them deflate to make sure your lungs are working right. We can also use this to kind of check how well does your blood circulation work, how well does your heart work. So they'll use them for other diagnoses too, but a big one has been using them to kind of search for cancers and making sure that people are detecting cancers at earlier and earlier levels so we can kind of intervene and remove them. So that's kind of a little bit about radioactive medicine, or one type of radioactive medicine, or one way radiation is used in medicine. And then the other way that radiation may sometimes be used in medicine is this idea of using radiation to purposely kill cells, using radiation as a way of actually removing cells that are unwanted. We already know that radiation over your whole body is really bad. So being exposed to whole body radiation, high amounts, is fatal. But if you took that same amount of radiation that would be outright fatal to a person and focused in on a really, really, really narrow beam, laser beam or even smaller than laser beam size beam, you could make that same whole field of death only hitting a very small amount of a person's body instead. And by hitting only a couple cells, you could kill off those particular cells. And that's another way that radiation is used in medical treatments, as a way of doing surgery without having to cut somebody open, surgery without having to use knives or other tools, which could be really useful, especially maybe not for a leg, but if it was in somebody's head, right? You don't necessarily want somebody cutting your head open to get to a tumor, even if it's a really bad tumor. But head surgery is very dangerous. Surgery near your spine can also be very dangerous. So there are some spots that are, inoperable in some ways. So there's a few different cases where inoperable areas are not very good. So in that case, they'll use a beam of radiation to actually kill the cells that they're worried about. Oftentimes it's called external radiation therapy or external beam therapy. And it's a beam of often gamma radiation. And it's designed on, again, gamma radiation can be bad, especially whole body radiation. But if instead of doing whole body radiation, we just do it in a small area, then you can actually treat somebody. So we can just jump to that idea. So using radiation as a technique to actually kill off cells that are dangerous. Whether this is a tumor, it could also be other types of surgery that need kind of things removed, whether it's a cancer or other types of tissue. But this is also very useful for people who can't be surgery done. So something in your brain, again, really hard to do, something in your spine, really hard to do. But some people health-wise just can't undergo surgery. Surgery is really hard on a person. They take you, they knock you out, depending on what type of surgery it is. They may stop your heart and have a heart or lung be bypassed and used being for a machine because of where the surgery is. And then recovering from all of that, in addition to just the recovery time, the drugs and the medication, it can be really hard on some people, and especially really older people or people with not very good immune systems or not very good health-wise. The surgery itself they may not survive. Just the act of stopping their heart or stopping, knocking them out and doing those different treatments, they may not survive that, and they're deemed inoperable for those restrictions. But rather than doing a surgery that requires knocking somebody out, potentially stopping their heart or lungs or other types of lengthy recoveries for cutting somebody open, or because of where it is. It's in your brain, it's along their spine. It's an area that would require just multiple cuts that are very deep and wouldn't heal very well. They could use this alternative where they don't have to cut you up. They don't have to actually even knock you out in some cases. You can be conscious for these. And it's not very painful. So it's not like doing surgery on somebody that, they're cutting your arm open and you're awake for it. It's a beam. It doesn't feel very painful. It's just a little warm. And it's very fast too. So it's not like you're sitting in the same position for hours and hours. It's relatively quick. So this is really useful for those types of scenarios where conventional operation surgery would not be a good outcome. So there's an alternative method of doing this using beams of radiation. Other benefits, right? You're not radioactive afterwards. You're hit with a beam, but just like if I shine a light at somebody, they don't stay glowing from the light. If you go out on a stage and you're in the spotlight, then you get off the stage, you don't still glow, the light goes away. Same thing for the radiation here. The radiation is only there for a couple seconds and then it's off. So these are kind of some benefits for these types of surgeries. And what they do is oftentimes they'll use multiple beams. So they actually kind of have you lie in one spot. And they'll actually kind of, just like if you have multiple lights, you can have something get hit with a light, from multiple angles. They'll do the same thing where different lights kind of cross through different spots. And as the light goes through, they have the light kind of hit a common location. So maybe you have one beam start right here and go through, and then you have another beam start up here and go through, and then you have another beam start over here and go through. Maybe you have another one go this way, another one go that way. And they basically all hit the same area, and that one area gets hit with multiple beams, and that one area that's been hit by multiple beams is going to get a kind of really high dose or even a fatal dose. But that's the area that you were trying to kill off, versus every other area, it only got hit by one or two beams. It's not that damaged. So they're able to minimize the damage to your healthy tissue by kind of moving these detectors around and having these sources kind of go through different spots. And that's kind of what that cartoon picture's showing. Sometimes they do this over multiple days too. So they do one treatment, you come back a couple days later, they do it again, you come back a week later, they do it again. And that's where sometimes they want to make sure they're hitting the same spot. They may give you a little tattoo. You'll have a couple little dots that they use to kind of make sure they're hitting the same spot. or they'll make a mold and they'll have your arm sit in that mold. So you're always putting your arm in the same position. Or they wear a mask and the mask kind of helps hold your head in the same spot. Because you do have to stay very still, even though it's only going for a couple seconds, right? You don't want to move and make the spot move because that would hit a different spot there. But these are different ways of kind of treating people with radiation that would be normally very fatal, but we're hitting only a very small area. We're only hurting that one spot. And we're going to use gamma radiation because we want to go through everything. We don't want to get blocked by anything in the process there. But you do have to keep people still. But the benefit is that a lot of people can't have surgery. This is a way to give surgery to someone who may not have otherwise been able to get it. And that can be very useful, especially for people whose surgery isn't a good candidate, either because of where the tumor is or because of their own health conditions. It can actually give 10, 20 years ago, this would have been considered a lost cause. Now there's something they can actually do about it because of these types of treatments there. So that's kind of one way of doing the radiation, right? Bringing the person to the radiation source, hitting them with a very small amount of radiation, and then they go home, and then maybe they got to come back a few times. But the other two methods, if you know where the tumor, if you wanted to again know where that tumor is, you could actually put something there that is radioactive near that tumor and actually cause it to be damaged that way too. And there's different benefits to doing this versus the other one. This may be, this is like surgery, but it's not quite the same type of surgery. It's more like laparoscopic surgery where they go in with small incisions and little cameras and they put something there. So maybe there's something they want to remove and they want to cut it out, but they don't want to use a beam because it's a little too big. What they'll do instead is they'll sometimes just take a small piece of material and they'll put it right on top of the tumor. So this tumor is getting, it's got a piece of radioactive material sitting right on top of it. And that tumor is being exposed to that radioactive material, often now giving off something like alpha particles. Those alpha particles basically damage everything that they're touching in terms of this material. But because this is sitting directly on top of a tumor, the tumor absorbs all that radiation and dies. Versus the rest of your body is pretty far away from that source, very low damage to the surrounding tissue, no worse than the damage from doing the initial cuts. So this is another way of kind of handling somebody for things, and this is kind of internal therapy. So either external, where you hit them with a beam from the outside, or internal, where you actually put the material right next to the tumor. And they'll leave it there for a little while, and then usually they'll just come in a few days later and they'll pull it out. They could either leave it for a few hours, or maybe they leave it for a few days, or they'll actually design it to be a material that breaks down over time. And after a couple of days, it breaks down anyway. They don't need to worry about removing it because it's non-radioactive. So they'll kind of pick the half-life and they'll design this so that it actually goes away after a short amount of time. But basically putting radioactive material inside a person right on top of a tumor or something that they want to kill off in terms of cellular mass is another way of doing radiation therapy as well. So internal therapy versus external. Only issue with that is that, again, you want to make sure that it's giving off the radiation near the source. So you don't want, now here's where you don't want a gamma radiation source. Here's where alpha is better, because smaller distances are better than long distances, because you want to minimize your exposure to everything else, right? So the thing near the source gets exposed, the treatment site gets damaged, but nothing else does. And then the only issue otherwise with this is that, there is a piece of radioactive material inside you. Depending on how radioactive it is, you may have to be kind of kept away from certain things. But again, it's usually only where the source is. So if it's in your leg, it's going to be in your leg, not near your head. But it's just something to be mindful of. But they could even design this to only have to do one surgery if they make it so that it is implanted, but then it breaks down into something non-radioactive over a couple of weeks. They choose the right half-life, and it's not radioactive by the time, a month later, 2 months later, it's all gone. And hopefully so is your tumor or other molecule they've been trying to remove. So this is kind of a different way to do that. It does do a little bit of damage to the surrounding tissue, but so would surgery, right? For surgery, when they go and open you up and remove that tumor, they're going to remove the tumor, but they're also going to remove the surrounding cells, because they're always worried, what if one of those cells, what if we miss a cell? So they do what's called a margin when they remove cancerous tissues. And the margin is any area that they think may also be cancer as well, because they don't want to have to do a second surgery. So conventional surgery also surrounds the damages surrounding tissues. So in that regards, this is very similar to kind of standard therapy. But again, you don't have to be knocked out. You don't have to have major surgery. You can do this by kind of doing an alternate way of treatment than the conventional surgical interventions there. But both of these techniques require you to know where the tumor is, right? You have to know exactly where the tumor is to fire this beam. You have to know exactly where the tumor is to put this material on top of it. And that's great if you know where the tumor is. That's where the idea of those imaging techniques, right? All these different imaging techniques that we were talking about before help us know where to do that surgery. But there's a newer technique that's been kind of used now more recently, is that they design those drugs, right? We talked about there's some drugs that will find tumors on their own. They kind of get attracted to tumors. And they've been trying to design now drugs that basically find the tumor automatically. They're attracted to that tumor. And then when they find that tumor, they actually are radioactive enough to kill the tumor, but no other cell. And the cool thing about this is you don't need to know where the drug is, because the drug knows where to go by itself. You don't have to know where to inject the drug. You just let it go through the bloodstream. You don't have to know where to go. The only thing is you have to know what you're looking for. So they've been kind of, if you know where the tumor is, beams are great, or implantation is great, external radiation or internal therapy. If you don't know where the drug tumor is, but you know what you're looking for, you can actually design these kind of hunter-seeker drugs that hunt out the tumor in your body. They hang out with it, and then they damage it when they're hanging out there nearby. So it's a kind of brand new treatment, kind of antibody-based treatment or other types of hunting-seeking technology treatment. Sometimes it's called systematic therapy. And again, it requires a lot of medical knowledge of what you're looking for. But if you do have that, maybe because you have a family history of a certain type of tumor, or they're able to do some other kind of scans and they know what they're looking for, they can design these basically custom drugs that will look for and remove the tumor by reacting with it chemically. The only issue that is, right, it's very hard to do. You have to kind of have a lot of knowledge, but we're getting pretty knowledgeable as a medical community for that. But the other issue is that the stuff you're injecting it, maybe you're getting it via IV, maybe you're eating it. It's in your body. It's moving around your body, trying to kind of find the tumor that it's supposed to remove. So in the meantime, while it's in your body, there is quite a bit of material that you are releasing. So your urine, your sweat, your saliva, basically your fluids have radioactive material in them because it's moving around. So you do have to be mindful of that. Similar actually for people on regular standard chemotherapy. Non-radioactive chemotherapy also, just the drugs are very potent, the drugs are very strong. So for the first day or two after your chemotherapy, when those drugs are in your system, you got to be careful about what you contact, because your sweat and things like that can be releasing that drug too, while it's also killing the tumor. So very similar to conventional chemotherapeutic drugs, you have to be a little bit careful, a little bit mindful, because you're releasing drug. You can also refer these radioactive drugs, rather than just releasing drug, it's releasing radioactive drug instead. So that is the one downside to this type of material being used, very similar to conventional chemotherapies. But also, if you know what kind of molecules you're looking for, if you know what kind of cancer you're looking for, this can be really nice because it'll find cancer in ways you don't expect, right? So you may expect the cancer to be in a certain region, but if it has spread to somewhere else, this drug will detect that. Versus if you're only treating one region, you wouldn't even know to check there to use those beams. So it is a different way of treatment, kind of a little bit different than the usual ones, but these are some of the ways that radioactive materials are used as medical treatments for various types of cancers, for various other types of surgeries, surgical interventions, things like that. And it's a nice use of these things. It's kind of the reason why we want to learn about being safe with our radiation, right? We don't want to be exposed needlessly, but when we do need to be exposed to something for a therapeutic, it's nice to have these other technologies to kind of help us find molecules that don't belong, help us find tumors that don't belong, and then remove them afterwards too. And that's kind of the use of the radioactive materials in medicine, is a lot of times for that. So that's kind of the big use there. And again, for these systematic internal fit systems, right? You want the internal ones to be giving off very low doses of radiation, hopefully something more like an alpha particle that's going to have a very short radius, right? So if this was giving off alphas, it's going to go to here. If it's giving off betas, it may go out to deeper tissue, may cause a little damage. So kind of alphas are better for something that's going to be internal, so that it's just doing less damage. It's still going to damage the tumor because it's right there, but it's not going to go as far as to hurt the other cells nearby that are still healthy. If it's a alpha versus a beta, they don't do as much damage. Versus a gamma, everything's going to get hurt. That would be really bad. So we're definitely not going to use gamma sources as our kind of internal treatment options. We're going to stick mostly with alpha, but if not, maybe you'll see some betas too, just because of the chemistry needed for those drugs to work. And lots of different ones are used, and a lot of times they're very short-lived. because they're used for internally. That way they don't even have to remove them later, versus the ones that are external, those can last longer because the external machine isn't inside you, it's not sticking around. But for the shorter ones, a couple days, it's already starting to break down. So after a week or two, it's all gone. And hopefully in that time, it's also killed all the cancer with it too, so they don't have to do multiple treatments there. So that's just kind of some examples. In surgery, a lot of medical techniques, and more medicine is using this type of materials. So just kind of being aware that they do exist. Be aware there are special safety precautions, right? Keeping your distance, making sure you have proper shielding, whether it's because you're working with the material directly or you have a patient who is, kind of knowing the safety for those kind of things. But it's one atom turning into another atom for better medical kind of use there. It's also used in all sorts of industrial applications, power plants, things like that. Nuclear power is nothing really fancy. It's basically just a giant steam converter. Any power plant, they all work the same way. Power plants with the, except for the solar power plant, except for the wind power plant and the water plants, every power plant, basically you need something to get really hot, whether that's hot by burning oil, burning coal, burning wood, burning nuclear material. It gets really, really hot. You dump water on a really hot thing, you make steam. That steam turns a big motor, and this is where instead a wind power machine just goes directly to this place. Water power machines, they just go directly to this place too. But it's just ways of making electricity by turning a motor, whether that's being heated up water with electricity, with nuclear power, with radioactive materials, or gas or oil. They all work the same. We actually have nuclear power plants sort of nearby. There's one down Atlantic City South. There's a couple in Pennsylvania, but there's also plenty of wind and solar powers in New Jersey. There's plenty of oil and gas. We get a lot of power in New Jersey, but we do have a couple of nuclear power plants as well, kind of in the area there. If you didn't know about that, we can skip that. So that's kind of the idea of the radioactive materials. And there are lots of atoms that are radioactive because they're different levels of stability. Some atoms are more stable, some atoms are a little bit less. But we can always find generally isotopes that will make that molecule to be radioactive. So we can most elements have isotopes that are radioactive. It's just maybe not the naturally occurring ones. They don't occur very frequently. They don't happen very often, but you can make them for things like medical purposes or for hospitals. So if a hospital needed a radioactive version of fluorine for something, there are ways to make that for drug purposes. And things like that. And it's often done at actually facilities that are pretty big. So it's not the easiest thing to do. You basically got to move atoms around really, really fast and then crash them into other atoms. So if you wanted to make your own radioactive material, you can, but you need a special facility to do that. These are cars, so it tells you kind of how big this place is. But there are ways of making those if it's needed for kind of medical use. So hospitals that need access to these things, these are usually very big labs. They're doing other kind of research as well, but hospitals can get access to kind of get the materials they need for that. But medical uses of radioactive material is really important because it's allowing us to do a lot more treatments than we used to be able to do than ever before. So it's kind of nice for that. And it's not it's much more safe than it used to be too. We've been pretty good about kind of making sure we're not exposing people needlessly to various conditions and exposures. So that was it for that. And we just got to be careful. Oops. I'll turn this on in a second because it's apparently not showing. Come on, turn back on, maybe. We just got to make sure that we're not exposing people to other stuff in the meantime. Thinking about it. There we go. But that's kind of the idea for radioactive materials. Kind of as long as we're careful with material, as long as we know what's going on and we're not exposing people needlessly, we're going to make sure that we're being safe and things like that. But that's kind of that chapter about elements. So we talked a lot about elements themselves. We talked about atoms, what makes an atom behave the way it does. It's all the protons. So the number of protons an atom has kind of controls its identity. And for the radioactive reactions, right, that's when you have one element changing its proton number and becoming a different element. That's how these processes can sort of happen there. But elements aren't just on their own, right? There's a lot of elements on their own, but elements will combine. And rather than having a single element on its own, it may combine to form a new material, something like a water molecule or something like a sugar molecule, where different elements have kind of interacted and formed their own new material that's a pure substance there. And that's this idea of bonds and molecules coming together to making new compounds. And they can do this either, it has to do with their electrons. Atoms are kind of interacting on their electron level. We talked about kind of protons, neutrons, electrons before. Electrons are the things around the nucleus. So nucleuses are here, electrons kind of stick out further, and those electrons that are further away are actually going to interact with other electrons, and that's how atoms can actually join up and form larger materials than just an individual atom, but they'll actually link up and form molecules that are multiple atoms together, forming this new kind of material called the compound. And just like elements are pure substances that you can't go any smaller than a given atom, molecules are kind of the same. You can't go smaller than an individual molecule of something and still have that same property. So something like a water molecule, two H's and an O have linked up together, and they form this new material that has different properties than water, than oxygen did, right? Oxygen is an element. It has its own unique properties. Hydrogen is an element. It has its own unique properties. And then H2O, water, has its own unique properties as well. And that's because those oxygen and hydrogen atoms have joined together and formed this new material, this new compound there. And the properties of those compounds are often different than the properties of the atoms itself. But if I were to try to cut this compound any smaller and cut off a hydrogen or cut off an oxygen, then I wouldn't have two hydrogens and an oxygen anymore. I'd have a hydrogen, oxygen, and then a free hydrogen. And then that free hydrogen would just be a hydrogen atom. It would be different than this water molecule here. So molecules are when you've combined atoms together, making a new thing, and they are pure substances as well. But why do these atoms come together, right? Why does a molecule of water come together and form this particular new substance? And that has to do with kind of the properties of the electrons. So the electrons are actually going to allow these hydrogens and oxygens to link up and form a new material with new properties there. Because we only got 118 elements. So we're kind of limited in terms of pure substances on the elements side. But once we start combining elements together to form compounds, we have a lot more options. So whenever we're talking about elements, we're combining elements together to form compounds. They're always going to have the same formula. So every O2 molecule or every compound of O2 is going to be two oxygens with the same properties. CO2 right here, that's a different molecule here. It also has unique properties, and it's got unique properties because it's got that one carbon and the two oxygens together. So just like how every element has a unique number of protons and that controls the properties of that element, every compound has a unique formula, and that formula kind of controls the properties of that particular molecule or compound there. So lots of different kind of compounds can form. And this is kind of just letting us show again that the difference between a compound and a mixture, right? You could just take oxygen and hydrogen, mix them together. This would have the properties of oxygen and the properties of hydrogen. It's just two molecules or two atoms together. Versus a compound, those atoms have actually linked up together and formed a new material with bonds between them holding those elements together. So when you grab this oxygen, the water's come along for the ride with it. Versus over here, if you were to grab one of these oxygens, everything else would stay behind. So atoms have combined together to form compounds which have new properties, and those new properties are coming about because those atoms are actually linked together. And they link together using their electrons. We talked a lot about protons before, because protons control the identity of the element, right? Whether it's oxygen or hydrogen or any other element has to do with what protons are present. But then once you have those elements present, they have other stuff too. Elements also contain protons, elements contain neutrons, that's in the nucleus. And then around that nucleus are electrons. And the electrons around one atom can interact with the electrons around another atom. And those electrons, depending on how well they interact, can actually form a new molecule through a new connection. So in this case, the oxygen and the carbon, the electrons around the carbon, the electrons around the oxygen, they get close enough together that this forms a connection. And this oxygen and carbon are connected, and then the same thing on the other side too. And you have this new kind of group of molecules connected together. These three elements are now connected in such a way that they're sharing properties, and they create a new substance with brand new sets of properties in terms of its physical and chemical natures there. So lots of compounds can exist. Just like how lots of elements exist, lots of compounds can exist from all the different kind of combinations of those molecules there. And the reason why they're holding together is because of those electrons. So those electrons are being shared between the different elements. Sometimes the sharing is really good sharing. The elements are really kind of sharing their electrons really equally, kind of like holding hands, walking around together, versus other times the elements are not so good sharers. Some elements actually are not very good at all at sharing, and they actually take electrons from other elements. And when they do that, they form a bond too, but it's a bond created by stealing an electron and being stuck together that way, versus a more mutual sharing where the two electrons are hanging on to each other, kind of being shared between the two different atoms. So a couple different ways of forming bonds, and we'll talk about both of them, but they all have to do with electrons. So they all have to do with the electrons around the atoms and how those electrons are interacting. If it's a more shared interaction, that's one type of interaction. If it's more of a stealing and taking type of electron or a giving and taking type of electron, that's a different type of relationship in that between those atoms, but that can also form bonds and hold those molecules together. So kind of the first one we can talk about, right? Sometimes atoms, they don't have the right number of electrons. They either have more electrons and they're more negative, or they have less electrons and they're more positive. So we know that that can happen from before. So ions are just electron containing elements that either have too many electrons for their number of protons, or they have too few. And if you have too few electrons, you're a little bit more positive than you otherwise would be. And if you have not enough electrons, then you may be a little bit more negative. And these are just some different examples of ions that we've seen already, right? We've talked about ions where the electron count's a little bit off. So if you knew how many protons were supposed to be in an atom and you knew how many electrons were in that atom, you could figure out, is it the same number? And then it's 0. If there's more electrons, it's a little bit negative. If there's less electrons, it's a little bit positive. Sometimes it's 1 more positive. Sometimes it's 2 more positive. May even be +3 or +4. Going the other way, it could be 0, but -1, -2, -3, -4 are all possible charges too. So whenever atoms don't have enough electrons, they're going to have either positive or negative charges on them. And we see that happen with different kinds of elements. And this is just some examples here. We've talked about that before too. So just if you ever want to count it though, right, you'll get the atomic number, right? You could look up the atomic number of magnesium, figure out how many protons it's supposed to have. They would probably tell us the number of electrons too, subtract those and see, do we get a positive number or a negative number there? And a lot of times atoms will form those electrons on their own, or they'll form these charged molecules, especially when they start interacting with other atoms. So that's kind of one idea of looking at atoms directly. But the other thing about atoms is they have a lot of electrons, right? So something like oxygen has 16 or 8 electrons. So 8 electrons and 8 protons. This one may have 10 electrons to get to a -2. But as you get bigger and bigger, you get more and more electrons. So something like a lead atom has 82 electrons. That's a lot of electrons to have to keep track of. And it turns out for atoms, usually the only electrons you care about are the ones that are the furthest away from the nucleus, because as atoms get bigger and bigger and bigger, their nucleus is the same size, but the kind of seating around them gets bigger, just like if you were to go to a concert, the hall, depending on how popular the singer is, the concert hall is going to be bigger and bigger and bigger. But for atoms, when they're interacting with each other, they're only interacting on the extreme edges. So the two atoms that are going to be interacting, it's on the outsides of the atoms. It's not the inside of the atoms. So the farthest away electrons are the ones that matter the most. So atoms don't, even though they may have 80 or 50 atom electrons, they only care about the ones that are on the farthest away from the nucleus, the ones that are the furthest out, which they call the outer shell, the electrons that are the furthest away from the atom. And those are the ones that actually control the properties of that atom. So the properties of atoms, even though atoms have tons of electrons, their chemical properties are often controlled by just a couple of electrons. So a couple of electrons and the number of protons really are what tell you all the properties of that particular element, what that element is, how it behaves, how it reacts with other elements around. And those outermost electrons are so important, they're sometimes given a special name. They're called the outer shell electrons. Sometimes they're called the valence shell electrons, or the outermost ones. So carbon's got a total of 6, but it turns out that only 4 of them are important. Oxygen, same thing. Oxygen's got a total of 8 electrons, but it turns out that only 6 of them are important. The other 2 are relatively unimportant for behavior of that atom. So we don't care about them. We don't look at them. We call them the outer shell or the valence electrons. And it's basically on an atom. If we were to look on our periodic table, the way it's arranged and shaped, the atom, the number it is over from the column. So so carbon's over here in red. It's 1, 2, 3, 4. If you're kind of counting across that row, or oxygen, it's 1, 2, 3, 4, 5, 6 across. And those values kind of can tell you actually how many valence electrons it has. So anything in this first column right here has 1 electron in the outermost shell or the valence shell. The second column going down, there's 2. We're going to skip the middle parts for now and jump all the way over here. Everything in this column right here, starting with the boron, going to aluminum, going to the rest of them ones down that line, they're all in that third column. They all have 3 valence shell electrons. And then the carbon line goes to 4, and then it goes all the way out to 8 over here. And that's something you can kind of tell just by looking at where the element is on the periodic table. So if we look at the periodic table and we know where our element is, we can tell how many outer shell or valence shell electrons there are just by its physical location for that. So that's kind of a nice thing about this periodic table. Remember before too, we talked about elements in the same column all have the same properties, right? Part of the reason why all these elements have the same properties is because they have 1 electron in that outer shell. Part of the reason that all these gases over here in the last column behave the same way is because they all have 8 electrons in their outer shell. So that's kind of a property for those. So atoms like that, for atoms, what we do, we call the valence shell electrons. We only care about if they have between 1 and 8. So sometimes for symbols and kind of make it easier to draw, what they'll do is they'll draw dots around these atoms to show how many electrons they have. And that can help us actually figure out how atoms interact with each other later. So all the atoms in this column right here, we could draw with a single dot to represent that 1 electron from that first column. The atoms over here in this column here, we could draw with 4 dots to kind of represent those 4 dots or those 4 electrons in that column. So carbon, being the 4th one right here in this 4th column with its 4 electrons, sometimes gets drawn as the letter C because carbon has C as its symbol, just like oxygen has O. And then they'll put 4 dots around it to let us know that this particular carbon atom has 4 valence or 4 outer shell electrons. Those are the electrons we care about. The rest of the electrons don't have much impact on the properties of that oxygen, so we're ignoring them for now. And same thing for something like sodium or lithium right here. Those are both in that first column right here. Sodium, Na, lithium above it, are both in that first column there. They all have 1 dot because they all have 1 valence electron. So we draw them both with 1 dot around them, even though they're different elements, right? So lithium is atomic number 3. It's got 3 protons. Sodium underneath it, atomic number 11, 11 protons. But they both are in that first column, so they both get shown with the 1 dot there. And this is a way of kind of what are called Lewis dot structures. Bless you. So Lewis dot structures are a way of kind of representing the electrons around those particular atoms. So we see that sometimes being marked and kind of noted for those. So ways of kind of noting. And then if you went all the way to the end, right? So if we went all the way over to this side right here, Ne number 10, atomic number 10, but 8 electrons around it, 8 dots. And they kind of show it. They usually put 2 on each side. So top, bottom, middle, left, or top, bottom, left, right, kind of 8 total. And then same thing over here, kind of 1 or 4, kind of letting us know how many electrons that atom has in its outer shell. The farthest away from the nucleus, those are the electrons that are going to be involved in kind of bonding and forming this atom to react with other atoms there. So that's kind of a symbol system that we'll be using for a little while. We'll go over more of this on Monday. Yeah.
So about the row number, what does the row number do?
Doesn't do too much. So yeah, so which row you're in doesn't really do too much for these atoms right now.
So it's just the column?
Yep, yeah, columns only. Yep. So going this way down, and then skipping this middle section and then jumping over here to 3. So yep, so columns are important. And then atomic number is important. That's why that number is still there. But yeah, row doesn't really mean too much in terms of properties or things for now at least. So, but property-wise, similarities, families, or columns, very important. So that kind of tells us. And even on, I think the periodic table that we have for the test, I think they mentioned the numbers still. Goes 1, 2, 3 through 8 there.
Are there like IS2 plus 2 2?
Yep. Yep. Yeah, you don't need to worry about that. Yep. So yeah, so there's other ways of kind of noting them. You don't have to worry about the numbering systems there. Yep. So for us, all we care about is what column they're in. You don't need to worry about what the names. Yeah, so every single column has its own name, basically like a seat chart. So there's a seating chart for the entire periodic table, and they all have kind of numbers for them. But for us, we don't need to know what the chart was. We just need to know what their total is. So in this case, that there are 4 or 6 there. So just the column spots are important. Yep.
So then for that example with the oxygen, you just need to know that it's in the 6th row to write 6
Yeah, 6 electrons. Yep.
around
Yep.
it. Okay.
Yeah, and yeah, there's 6 dots, and if you wanted to know what the dots were, these are the codes for each one. Like, so 1 dot is 2s1, 1 dot is 2s2, but it's just kind of like the seat number for the row. So yeah, so they every electron kind of has its own special space to go in an atom, but we don't need to know which one it is. We just need to know that there's 8 seats there. It doesn't matter which seat number it's in. So yep. So don't worry about things like the exact number, code convention, things like that. Just know that there are spots for those electrons. And when you fill up all those spots, right, when we fill up all 8, we got to go on to the next kind of atom, right? So if we go to the next row, then you get to the 1 again, right? So it goes to 8, and then you go on to the next column, and now we're back to 1 and 2. We'll skip all these, jump to 3 again. So we're kind of constantly adding more and more electrons as we go along. So that's kind of the idea for these particular atoms, these particular structures. And again, ions are just when we have atoms that have extra electrons. So if you were doing this dot diagram, you may draw Na like this, or you may draw Na with an extra dot. And that Na with an extra dot now has 1 more electron than it's supposed to, and it's going to become negative. Or maybe instead I have an Na and I pull a dot away, I take a dot away from it. And then that also is going to become positive now because it's missing a dot. So those dots can sometimes help us see, as long as we know what it was supposed to look like. And then we look at the new drawing and we see it either has more dots or less dots. Then we can say, oh, this is a O2 ion. It's missing some dots, or it's got some more dots and it's got either a negative or a positive charge. Because usually what's happening is these atoms, right, having dots is great, but there's certain numbers of dots that are better. And from an atom standpoint, having either 0 or 8 dots is kind of the best possible scenario. So this Ne is really, really happy. It's got 8 dots around it. It feels pretty cool. This sodium is a little upset because the sodium either wants to have 8 dots or no dots, and it's got 1. Carbon up there is really kind of in the middle. Carbon wants to either have no dots or 8 dots, and it's got 4. So it can either get 4 more or it can lose 4. But either way, it's going to try to get to 8. And same thing for sodium. Sodium's going to try to get to 8 or 0. It may give away an electron. It may take more electrons instead. And these atoms trying to get to 0 is going to be what drives them to form ions. So chlorine is going to try to get to 8, and it's going to try to get to 8 by picking up an extra electron. Sodium is going to try to get to 0. It's going to get rid of its 1 electron to get down to that 0 point. Same thing for magnesium. It'll get rid of some electrons until it's at that positive, or positive 2, which happens to be when there's 0 dots around it. So atoms are oftentimes trying to get rid of extra electrons. And so sodium here, or lithium here, they're going to try to get rid of that, and they're going to become Na plus or Li plus. Because then it has 0 dots instead of 8, or 0 dots instead of 1. And 0 dots is way better than 1 from the sodium's perspective. So we're going to see sodium forming ions whenever it can. But to do that, it's got to give this electron to somebody. It can't just drop the electron on the ground and hope that somebody else finds it. It's got to make sure that that electron goes to something else. So sodium's going to be looking around for atoms that might like to have an extra electron. And if it finds one, it'll give that electron to something else, and it'll become Na with no dots, which is positive because it's missing an electron. Yeah.
So elements that have too many electrons could give an electron to an element that doesn't have enough electrons?
Yeah, it could go the other way. Yeah, this carbon could start giving away or taking electrons. Sodium could go around and instead grab 7 more electrons, but that's just really hard to do, right? Because it's easier to get rid of 1 thing than it is to gain 7, because it would have to find 7 other atoms to get it from. But it could. And that's why kind of carbon's in the middle there, because carbon could go either way. So at some point it becomes easier to take, some point it becomes easier to give, and then there's a few that are kind of in the middle there. And that's why chlorine generally becomes negative, because it's a lot easier to find 1 than to get rid of 7. So it's easier to find 1 person willing to give you $1 than find 7 people willing to give you one. So kind of that's where it's happening. Or find 7 people willing to take something, and you can only give it to all of them if all 7 are there at once, because you can't go around with less than that either. So it's kind of getting the right numbers together. You'll see different kind of rates. So chlorine, fluorine, they're more likely to become negative versus sodium and magnesium more likely to become positive. But either way, we're going to form these ions. We're going to form ions with charges. There's sometimes actually special terms used for positive and negative ions. So if you're reading about something later and you see cations and anions, cations and anions are ions, right? They both have the word ion in their name. Anion is still ion, cation is still ion. They're just being a little bit more specific. So a cation is a positive ion, an ion that's positively charged. So something like Na plus or Mg plus or K plus. Those are what are called cations. And then anions are just the negative version. So an anion is an ion, but it's an ion with a minus charge. So oxygen and sodium ions are both ions, but oxygen is an anion, sodium is a cation there. So if you do see those terms, that's where that comes from. So cats have paws, right? Cats have paws. So cations are the positive ones. Also, right, a T kind of looks like a plus. That's another trick, right? So T's kind of look like pluses. Anions have an N for negative. So there's various ways to remember one. Usually you just remember what one is, and then you know the other one's the opposite. But if you do see the word cation or anion, those are just referring to a specific type of ion that exists. But they are both just ions, right? A cation is still an ion. An anion is still an ion. It still has a charge. It's just being a little bit more specific maybe than we would otherwise be. So that's kind of something you see. And then the idea is, right, so there's 2 ways that sodium can get to 8 or fluorine can get to 8. All these atoms, they're trying to get to a total of 8 dots. And it's just some are a little bit easier than others. And this is kind of the 2 extreme examples, right? Fluorine's got 7 dots. If we were to go back to our periodic table, we would see fluorine over here. Fluorine's the letter F. It's in the 7th column there, the 7-dot club. We've been using sodium a few times. Sodium's over here on the first one here, first column, first dot club there. So, right, so this fluorine's got 7 dots, and it wants to get to 8 or 0. It could get to 0 if it could find 7 other atoms willing to take an electron. And that happens sometimes, and you'll get fluorine 7 plus. But it's a lot easier, rather than looking for 7 things, it's a lot easier just to find 1 thing than 7. So it's a lot easier for fluorine to give away or take 1 electron from somebody else who doesn't want one than it is for fluorine to find 7 things that would like one instead. So oftentimes you'll see fluorine forming this -1 charge. And then the same thing or opposite thing, in fact, happens with the sodium. So sodium has 1 dot, it's trying to get rid of it. And it can either look around for 7 things that are giving away dots and gain 7 electrons for a -7 charge, or it could look for 1 atom, like a fluorine, that is willing to take an electron. And there's lots of atoms willing to take electrons, so sodium gives its dot to that atom. So in this case, the sodium is a good partner for fluorine, right? Fluorine wants an electron, and sodium doesn't want an electron. Sodium has an electron to give away. Fluorine is looking for somebody willing to give away electrons. And sodium and fluorine will actually combine together. Sodium will give its electron to the fluorine, and you'll end up with an atom that has the electrons that it wants, right? Sodium then gets to be 0, which is what it wants to be. Fluorine gets to be 8, which is what it wants to be. Both of those atoms are happy. And that's actually how we can form bonds between different elements. Elements are going around looking for elements that have too many electrons. Some elements are going around looking for elements without enough. And if they pair up, they can give their electron to the other atom and form a new bond. So a molecule can form between the sodium atom and the fluorine atom by forming these 2 ions and transferring their electrons. And that's kind of the idea of molecules forming from ionic compounds or ionic interactions. They're ionic interactions because they result in ions, right? F minus is an ion, and A plus is an ion as well. And generally, we can predict what kind of ions happen, right? Because fluorine can either form F minus or F7 plus. Atoms are always going to take the easier route. So they're going to go in the way that's the easier job to do. Gaining 1 electron is easier than losing 7. So basically, whatever results in the smaller charge. So 1 is less than 7. So when you have to choose between +7 and -1, go with the -1. when you have to choose between +1 and -7, go with the +1. So go with the smaller of the two options. That's usually a sign that that's what we're working with there. So that's kind of this idea for atoms for forming charges, forming molecules, for forming results there like that. And this is kind of an example of doing that. And basically, you can predict the charge by the row it's in. So the first column right here is going to be +1. Second column is +2. Third column is usually +3. And then when you jump to the other side, same thing happens. -1, 0, -3, things like that. So that's kind of our example of doing that. And we'll see this next time too. We'll see things, some of the ones in the middle, again, don't worry about. Middle ones are a little weird. They're a little bit harder to predict. But if you're in the first 3 columns or the last 3 columns, it is something that can be kind of predicted there. And even something like, right, like an oxygen or other atoms, just kind of, yeah, this is a good example. And we'll start up with this again next time on this idea. So something like this oxygen, right? If you were to look for an oxygen on the table, find one, it's right there. It's forming that oxygen minus oxygen spot. It's in the 1, 2, 3, 4, it's in the 6th column there. It's got 6 dots around it, and it wants to get to 8. So if we can put 2 more dots around it, we can go from 6 to 8. And that means it has 2 more dots than it's supposed to be, gives it an overall charge of a -2. So we'll start up with that next time. We'll kind of finish kind of going on from there. But that's that idea of kind of looking at atoms, figuring out charges, figuring out how atoms interact with each other. So it's a Wednesday, so have a really good Wednesday. We'll see everybody on Monday again. We'll go over stuff for test 2. So if you have any questions about test stuff, bring it. You can also email